Hey everybody, in this video we are going to do the most just straight to the point, what you need to know, memorize, and understand to successfully graph foundationally a rational function. There are going to be cases that arise with weird things happening, but what I say in this video today will remain true for all of those situations. Okay, so I've color coordinated things right now, and I will continue to do so as I graph. I wrote the example, very simple example, but I wrote the example down twice because I'm going to highlight blue and green on one, and I'm going to highlight yellow and pink on the other one. If you notice in the yellow, I'm only referring to this as really end behaviors. I think calling it horizontal asymptotes is stupid for a few reasons. One is it's misleading in the sense that people think that like a vertical asymptote, you can't cross it, and that's just not true. Two, it isn't always horizontal. It could be linear with a positive slope or a negative slope. It could be quadratic, cubic, quartic. Your asymptote, your end behavior can be dictated really by any of those. And also because if you consider end behavior, it is consistent even for the cases that end up working out to not really have a dotted, invisible imaginary guideline, more so a actual solid graph. So I will avoid calling it that. I always learned it that way, but I think it is misleading and confusing and causes more harm than good. But I know that many people have been introduced to it that way. And despite me telling them you can cross a horizontal asymptote and it's not always horizontal, it doesn't matter. Every time, even my smartest students will still be like, wait, but what? I'm crossing, and confused. So that's going to be a big issue. Okay, so this is part of the notes. Now this little layered boxes are on purpose. So I'm going to kind of go through what to do in a bunch of these cases, and I'll model it, and then I'm going to do a ton of separate example videos, but I will follow these rules and I'll try to color code it all the same way as I have this set up right now. So first thing, the numerator. If you can factor your numerator, you're going to do so. This is already prime in a way. It's linear. I can't factor it unless you wanted to take out the 2 and make it 2 parentheses x minus 4.5, but you know, whatever. From factored form, typically you would need to put it in factored form, right? Set each factor equal to 0, solve for the x-intercept. So if I set that equal to 0 and I solve for the x-intercepts, right? Add 9. Divide by 2, you get 4.5. So on this graph, 1, 2, 3, 4.5. Right over here, 4.5 is my x-intercept. Okay. Multiplicity of the factor determines the behavior at the intercept. There are always invisible parentheses around any numerator or denominator. So even if they're not there, you have to know they're implied. Multiplicity is the exponent on the outside of a factor. That is multiplicity. You should have learned that in Algebra 2 on your unit on polynomials. You should have learned about multiplicity at that time. If not, learn it right now, okay? If you're in my class, we just did this like a few weeks ago. It's the beginning of this very same packet that we are taking notes on now. Now, the multiplicity of the factor determines the behavior at each intercept. Okay, in blue, let's go over here. This is sort of like a footnote regarding the numerator, the x-intercept. LB stands for local behavior. LB stands for local behavior. That doesn't mean end behavior. It means what it says, local. It means at the x-axis, how does that intercept behave? It's going to behave like the house it grew up in. The house it grew up in is the factor. If the factor is to the first power, your x-intercept will behave like a linear equation when you're really zoomed in and close. If your factor is to a second power, it's going to look like a quadratic. It's going to be quadratic behavior. Now I'm going to indicate this with an L, a Q, or in this case, a C. And it's going to behave like a cubic. Now, sometimes cubic and linear kind of look alike, but you have to also remember it's at the intercept. If your graph gets close to the x-axis and doesn't touch it, don't get confused. But that's quadratic. No, it's not behaving on the x-axis. That is just, it's turning around. It was a dead end, couldn't cross the x-axis. It's turning around, okay? It has to be at the x-axis, how it behaves at the x-axis. Now, if you notice, I stop at third power. Fourth power is going to look like this, but it's just ever so slightly flatter and so on. And same with the cubic. It's going to get a little bit like flatter, more squared off in the between. But for all our purposes, for what we're doing, honestly, it is good enough to think of it, just as it is. So we're going to typically see one of these, and we did this when we reviewed graphing polynomials, because finding your x-intercept for a polynomial is literally identical to finding your intercepts, your x-intercepts on a rational function. So going back to this situation, right? Just make sure I leave this important stuff. Okay, so I'm going to mark up my x-intercept. I'm going to write two things. I'm going to write 4.5 underneath it, and I'm going to write L for linear above it. I've been doing this since God's dog was a puppy, and I write it down. I promise, not as experienced as me if you're in high school, because I've been doing this since before you were born. So trust me. Okay, thanks. So that is marked up. Finito. I'm going to do a little highlighting so we know that the blue information got us here. Numerator. That's why this box is going across horizontally at the top over here, okay? Next thing. Let's say I want to get my y-intercepts. To get your y-intercept, we typically think of it in expanded form. So in this case, factored form and expanded form end up being the same thing. And what you really do, it says evaluate x at 0 to find the y-intercept from any form. So really, you can do it from any form. And the reason we look at what I wrote there, the right side, is because if I fill in 0 for x, I'm going to do it in the bottom equation. 2x and x go away, and the only thing left behind is -9 over 3, the constants. Beware when your constant is 0. I promise this always works, but you might mess up. So don't, okay? -9 divided by 3 is -3. So my y-intercept will be -3. You never have to worry about like a form of how your y-intercept is an intercept. You can't bounce off your y-axis. You will always cut through it. Couple things to note. If you get 0 over a number, 0 on top, that's okay. It equals 0. That's the origin. That would probably mean you have y-intercept of 0, 0, as well as your x-intercept of 0, 0. So it should be both. If you get 0 on top only, that's a no. It's undefined, and it probably means you have a vertical asymptote over your y-axis and therefore have no y-intercept. But if you get 0 over 0, that is a special situation, which I will address later. Okay, those are labeled and done. Next, let's look at my vertical asymptotes, and those are going to come from our denominators. Please, on any assessment, on anything you ever turn into a teacher, you never, ever write just a number. You are writing ordered pairs, or you are writing equations. I'm labeling in the picture 4.5 and -3 on their respective axis. I don't need to write it as an ordered pair. But if they're floating around in your scrap work, you write it as an ordered pair. You label it. And your asymptotes are the same. So here, what does the green say? Denominator vertical asymptotes from factored form, set each factor equal to 0 and solve. These are your vertical asymptotes. Why? Because those are the places where x is undefined, or x causes the fraction to be undefined, the 0 in the denominator, right? And those are not in our domain. So what are we doing? We're laying down like caution tape. We're like, hey, don't go here, danger. And we're laying down dotted line to say, don't step here, you're going to fall. There's a crack in the ground, okay? You're going to fall down into the core of the earth, okay? So if I do that over here, I'm going to do the denominator right there. What do I get? I get my vertical asymptote is at x equals -3. You said it equal to 0 and solve for x. So I happen to get -3 again. I really wish I didn't do that where it worked out that way, but is what it is. So I'm going to label this as well. And it's always a good idea to really extend your asymptotes pretty far on your paper, because it's going to help you draw your graph, because sometimes, you know, it gets a little dicey. So I'm going to label, for one thing, -3 as my, so I'm going to maybe label x equals -3 down on the bottom somewhere, okay? I don't want to crowd up the picture too much. And I can't move that over more. Okay. The other thing is, in green, I'm going to go down to the bottom of the page again, right? Down here, AB stands for asymptotic behavior. How do your asymptotes behave? This is all. If you are testing your intervals to figure out where to draw your graph like a crazy person, you're welcome right now. You're welcome, and you're so lucky you found this video. Okay, so if the factor that you got the asymptote from is raised to an even power, that means the branches are pointing in the same direction. Think like a quadratic, right? So they're either both pointing up or both pointing down, and usually you have a clue to get one of the sides started. And if the factor is to an odd power, like 1 or 3 or 5, that tells you the asymptote that you got from that factor will have odd or opposite behavior along the asymptote, meaning your branches will point against that asymptote in opposite directions. So the one running along the asymptote, not running out to the ends, that's called end behavior. Along the asymptote, hence asymptotic behavior. And again, this is from your denominator, finding your vertical asymptotes and how everything behaves. So again, is this written with parentheses where I can see the power? No, but I have a brain in my head, and I remember learning since I was a little baby that it's invisible parentheses, so it's to the first power, okay? So I'm going to label this asymptote with, I don't want you to label it odd. I don't know why you guys keep labeling odd and even, like opposite or same. Like, what do you do when you get there? That's what you want to label it with. Just like the L, the Q, the C. What do you do when you get there? So when you're drawing and you get there, you left yourself a little note, a little clue to remind you of what to do when you get to that, right? Last thing, looking at leading terms. So I'm looking at the yellow now. So leading terms get us the end behavior of a polynomial. You look at your leading term, and if it's positive x to an even, the end behavior is up and up. If it's positive x to an odd, the end behavior is down and up. If it's blah, 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 blah. I hope you know the drill. So what we're going to do, left side of the equation in expanded form, we're looking at the ratio of leading terms. That decides your end behavior. It's not the be all and end all. Like, you with the brain have to finish putting it together. Okay, like, it's not like so idiot proof, but like you have to finish thinking. Okay, not everything requires you to be brainless, you know. So leading term over leading term in this case is 2x over x, and if you can reduce it, you're going to reduce it. X can cross out, so I'm left with 2. As x gets bigger and bigger and bigger, if this is y equals 2 right now that we're looking at, well, what does y equal? For end behavior, meaning way out when x is infinity and way out when x is negative infinity. There isn't even an x here. Y is 2. That's a constant. So what does that mean? Well, that means y is always 2. So your end behavior in this case is a horizontal line. It is not always a horizontal line, nor are we always required to not cross it. Your horizontal asymptote describes your end behavior and sometimes helps us draw our graph in the middle just ever so slightly. Okay, so I'm going to add the horizontal asymptote to my paper. Now, there's no behavior to worry about now on this. It is what it is. And that is the y value of 2 right there. All right. And now we have to draw. How do we draw the graph? Context clues, my friends. these 2 points over here, they got to connect, okay? The only place I'm not going to have graph is at the asymptote of -3, the green dotted line. Every other x value will have graph. Now these have to connect. That is linear local behavior. That means I'm going to cut through fairly straight. Then I'm going to approach my end behavior. Why? Because that's literally what it means. Your end behavior is telling you how does your graph behave as you continue to go out to the side. It could not be more literal. So as I go out to the side, I'm going to get closer and closer and closer to that dotted line. Now I cross through here at 3 because you always -3 because you always do, and then my vertical asymptote tells me I got to go straight down and never touch that. Now, is it possible I turn around and go up? Absolutely not. You are not the Kool-Aid man. You may not cross through the x-axis unless you were invited by a doorway or an x-intercept. Now the asymptote is up, meaning if I'm pointing down on this side of the asymptote, I will be pointing up on this side, and then that branch for the rest of the graph is going to stay more or less up here in this little corner, and it's going to ride along the asymptote forever. As it approaches the value of 2, it's going to get closer and closer to 2, and that is it. Okay, this is a very fundamental basic example. Now a couple things. What do these mean? If you get 0 over 0, that means, think of it as a little division sign. It's telling you could divide something out from the top and bottom. Now, where are we going to look for clues on that on this sheet? And if you don't have your own copy, you're going to pause and copy all this information down and make yourself the happiest little guide. Down over here, if I have 0 over 0, this tells me what happens. If the numerator and denominator, what is this dot? I don't know. If the numerator and denominator contain common factors, they are removable. Removable, what does that mean? Cross it out from the top and the bottom. Remove it, okay? I like to think of it, if you have a wall with a hole in it, right? Have you ever gotten spackle and you fill the hole with spackle and you wipe it with the little putty knife? This is like you're wiping the hole with putty knife. What hole? The hole in your graph. The graph will have a hole in it, okay? So the matching factors can be divided out to be 1, anything over itself. However, the existence of this factor in the denominator, right, in the denominator, it still screws up our domain, and it still creates a discontinuity. So unlike an infinite discontinuity, which is your vertical asymptote, it's a dotted line going up and down towards infinity, and it's also infinitely stuck in your denominator. You can't get rid of it, which presents a vertical asymptote. A removable discontinuity presents as a whole. So again, you have a graph, and when you remove a point, you erase just a spot, okay? It makes a hole in your graph, presents as a whole. Now, you only know the x value of the whole. So to find the coordinate point of the whole, set the removable factor equal to 0, solve for the x coordinate. That's your x value of the whole. When you set that factor equal to 0, cross it out, it's gone. Don't make it an x-intercept or a vertical asymptote. It cannot be both of those things. Rewind that right now and listen to it again 3 more times. I'm not kidding. Do it right now. Remove the removable factor. It is dead. It is gone. It is not anything. It is not a vertical asymptote. It is not an x-intercept. If you get something happening, 2 things at the same time on your graph, you screwed that up. Evaluate the remaining rational expression. So after you cross it out, add that x coordinate, and the result is the y coordinate of your whole. So you'll see that in these examples. Okay, I'm going to do examples in other videos, but this was your notes. Okay, this is what you need to know by yourself with your brain because you're smart. So make sure you know it. All right, and have it copied, memorized, whatever it is you need to do, because at some point you'll have an assessment on this. Promise. Questions, comments, concerns, feedback, whatever the heck you need in the comments, please. If you appreciate this work over here of me putting all this organized for you to hear again, because sometimes 5th time's the charm. Thumbs up. If you hate it anyway, thumbs down. And I'm going to put a thumbnail to the playlist on all sorts of rational functions, but I will be adding right after this video a ton of videos very tailored to this method and color coding the same way. So look for similar thumbnails. And I'll try to put them in the description box at some point. Oh, you need to review long and synthetic division. I will put that in the description box for you as well. Okay, bye. Adios.